Well, thank you, Simon. And no, pleasure to be here, particularly at the first meeting. I seem to have done, like everyone, 2 years of Zoom meetings, and for me, it's delightful to actually sit down and have some people in the same room. So this is a pleasure. Um, this evening, I'm going to talk to you briefly about Fluorspar. Now, Fluorspar is a strategically important industrial mineral that everybody uses every day, and I suspect most people, when I'll ask for hands, don't know that they've used it today, but you have. Um, why am I being so confident? Well, quite simply, because if you open the fridge this morning, the refrigeration gas that keeps the fridge cold requires Fluorspar. Air conditioning requires Fluorspar. Aluminium, it is aluminium fluoride is a flux that reduces the cost of smelting aluminium. And going forward, it doesn't lose its importance because although most people are getting giddy with excitement about the electric car and lithium, what isn't commonly known that there's a lot more fluoride or fluorochemical in a lithium-ion battery than lithium. Why do I say that? Because one of the problems with lithium-ion batteries is they've got to be fire resistant, and fluorite makes fire resistant plastic coatings, and there's an awful lot of fire resistant plastic coatings in the electric car, in lithium-ion batteries. And then if the research boffins around the world get their act together, the fluorometal is emerging as potential for electrical storage that can store a lot longer electricity for a lot longer and reduces recharging rates. And there's so much research into battery technology with different raw materials, but there's certainly a big application for fluorochemicals within the electric car. It is a very important industrial mineral for which there is a short supply. What I'm going to do this evening is a quick run through the fact that we do mine and have consistently mined it for a long time, Fluorspar ore to make into acid-grade Fluorspar in the Peak District in Derbyshire. Let's see if I can make this work. No. Right. We're up in the Peak District where we mine the fluorite veins and produce acid-grade Fluorspar, and we're very important insofar as, although we're very small, because most of the chemical plants, fluorochemical plants, are in Europe and work on just-in-time delivery, we are supplied from a European mining operation with short travel time, and that makes us strategically quite important. Fluoride. Now, the Fluorspar veins in Derbyshire, and starting very briefly with the geology, they're complicated. They're a polymetallic vein, a hydrothermal vein that comes out when the limestone cap was formed. It created cracks, fissures, and faults, and it is hydrothermal liquids and gas bubbled up and formed mineralized veins within the limestone in northern Derbyshire. Now, why that has happened all over the Pennines, why the North Derbyshire limestone has got mineral-rich veins, I can't answer. But in the mineralization in the UK, there are two locations primarily with mineralized veins. The first is in northern Derbyshire, and the second is in Weardale in the northern Pennines. But sticking to where we are in Derbyshire, effectively the faulting system is east-west trending hydrothermal veins that extend from surface to the overlying, through below where the shale cap is, to the underlying volcanics. The veins range in thickness from 2 to over 15 meters with a grade of 15 to 50% CAF2. They are polymetallic, so we have multiple minerals. In the vein systems we have in Derbyshire, we've got 3 mineral targets. We've got calcium fluorite, we've got barium sulfide, which is barytes, and lead. They've been mining lead. We've been mining lead in the Peak District since Roman times, and it became very important during the 1600s when it was the main source of armaments. And lead mining in Derbyshire was prolific because it was the main source of armaments. But at that time, the old miners were only interested in lead, and the other minerals, barytes and fluorspar, basically was discarded. We only started mining fluorspar this century, and we went back into the old lead mining areas and the other veins, and recovered the fluorspar ore and barytes. We had a polymetallic ore, and the current processing plant that was built in the 1965 and has operated continuously up to today. We mine fluorspar from underground in our Milldam mine, and we open pit. In our underground mine, it's effectively a semi-vertical, about 85 degrees vein structure. Unfortunately, there's nothing simple about fluorspar. The geology is complicated, and therefore mining becomes complicated. Although this shows a generic cross-section, the veins pinch and swell and vary and split, and it becomes very difficult to mine, and there's an awful amount of grade variation. But in simple terms, we mine it through a sub-level open stoping system where we build sub-levels at, we've got our mineralized zone is about 100, below the shale, and it's around 150 meters. We develop a series of sub-levels at an interval of 20 to 30 meters, and then we put in haulage drives in the host rock, and then crosscuts into sub-level open stopes, which are drilled where required with long hole, blasted down into draw points, and hauled to surface in a scoop tram and haulage system. And the waste rock is repacked into the workings. It's not packed as a paste fill, it's more packed for disposal. And we leave a series of both crown pillars and rib pillars to effectively prevent the shale from coming in and provide stability. We also mine the vein from surface we push the depths as hard as we can, but we will go down 100 meters in our open pit workings, and they're narrow vein open pits where we try to keep the footprint as narrow as possible. A long strike length, and we've developed a series of blasting and bench techniques because the limestone host on either side of the vein systems is strong. So we've developed a system of keeping the working areas very narrow and very steep. And they are mined conventionally with quarry techniques of drill and blast, backhoes load dump trucks, and bring the ore out and take it to our processing plant. The advantage of the open pit is our grade control. We can effectively broaden out, and we're able to then take stock work and replacement and lower grade material either side of the vein system. Underground, we have to be more selective to mine the main vein structures that are higher grade, because for the cost per ton of mining, we want more contained mineral because it's higher cost. So we try where we will allow in the open pit to have a cut-off grade down to 15% Fluorspar. Underground, we try and keep that higher to mid-20s, and we're looking for about a 30% cut-off grade. We then take the Fluorspar ore to a central processing plant at our Cavendish mill site, and this is shocks a lot of people when they come, because they tend to think we're a small, scruffy industrial minerals operation, and when they come into the mill and see how complex it is, it usually we're not regarded as the poor relation of the mining industry at the end of it. Primarily, it's a flotation plant, and we separate by flotation. And the system that we apply is we bring the ore in and we put it through a front-end crushing process. We're very fortunate insofar as the mineralogy. The mineral that we're looking for is soft, and the host rock, limestone, is a lot harder. So we can concentrate, and the words come in, and we are a classic mineral processing plant. So our first phase is through a series of crushing with some dense media. We concentrate the ore because we know that the fine material is where the mineral is, and we get good recovery by rejecting the oversize, and we produce then a washed limestone aggregate, which is a byproduct and goes to the cement industry. We then take, from crushing, it goes to grinding. Now, grinding is very important to us insofar as we have to create the right feed to flotation. We also put in we have regrind and recirculation to maximize recovery. This is where the complexity comes in, and cyclones to reduce the undersize. We then take from the grinding circuit, we then go into flotation. Now, this is where it becomes interesting, because we have a three-way flotation, polymetallic. We take out three mineral products in flotation, and Fluorspar is at the edge of being able to float. So what we're looking to produce is an acid grade concentrate, which is 97% fluoride. That's the easy bit, because if you don't produce a 97% CAF2, you're not in the game. What is the difficult bit is the 3% that goes in, because we have to control the contaminants in the 3%, very important, before they go into the chemical plant. Now, the problem we have, or the challenge we have, is that primarily the veins are lead rich. That's good, because the lead's worth, when we can recover it, quite a lot. So we feed to flotation, and our first step in flotation is to remove the lead, which we then sell as a lead concentrate to a local lead smelter in Derbyshire. But the challenge is we want lead in the ore because it's good revenue, but we don't want any of it in our Fluorspar concentrate. So we have to have a very efficient first phase of flotation, where we need to recover and take out all the lead, because we're hunting for very low lead within our Fluorspar product. The second phase of flotation is we take out the CAF2, which is what we are targeting. It's the bulk of our target. We then take from the rejects of the the CAF2 flotation, fluoride flotation. We then strip out the varieties, which is a floated varieties that makes a off-white filigrade varieties, which is a saleable product, and then the balance that's left goes to tailings disposal. And that's usually where a lot of my colleagues in the industry that visit us suddenly come out and say, this is not an easy processing plant, which I'm assure you it's not. So the Fluorspar ore that we delivered from our mining operations blended in stockpile, and then the aim is to create a steady state feed into the processing plant. We're really looking for an average of about 25%, but if we can have an average feed of 30% CAF2, that is where we're aiming. This is a typical we have a lot of variation, but this is typical of the ore feed that we produce. And we process the plant, it processes around 1,300 tons of ore a day. Looking at the statistics, we produce, in summary, an acid grade Fluorspar concentrate, which is what we ship to our chemical plants in Europe, mainly Italy and Norway, a lead concentrate which goes to local smelter. And the local smelter, that's interesting, it primarily uses recycled lead, church roofs, now I shouldn't say that, and other areas, but it actually does very well with a component of primary lead concentrate. It does better with having that as a combination with. We produce varieties which goes to the filler market and the oil industry as a weighting agent, drilling muds, and then stone aggregates. This is a typical Denver cells flotation working well. It's interesting with the strive for automation, and some of my colleagues elsewhere that have gone to fully computerized reagent dosing and taken away, a bit like fly-by-wire, partly for budgeting reasons and partly, I think, from experience. When we refurbished our flotation plant in 2012, we didn't go for fully automated reagent dosing to operate the plant. We used a series of peristaltic pumps because we still believed that the flotation operator's skill at adjusting the reagents and using his eyes to work out whether he got the right froth within the and agitation within the flotation cells are very important. And I've debated that with colleagues and a lot of them have said, formed the opinion that if you take away the skill of the float operator and replace it with a computer, that you can go a step too far. And we certainly regard one of our primary skills is the float operator and allowing him to adjust during the shift. I want to just say a little bit about tailings disposal because it's an area that's very important to us. When in Cavendish Mill we have 4 conventional tailings dams where we pump. The water is recycled, classic suspended solid settlement, and it is a very conventional tailings dam. The only difference to the hydrocyclone dams that create the dam wall with tailings is that we engineered our dam walls for safety, and so they're engineered structures, and then we contain the tailings. The 1 to 3 dams are fully restored, and our number 3 dam is generally regarded as a good example of tailing dam restoration. Now, I would just draw breath there and say that we operate in the Peak District National Park, which is highly sensitive, very high profile, and you couldn't permit a new mining operation there today, even if you had the time and patience to try. Our number 4 tailings dam was permitted in 1970, and it took 2 public inquiries and took years to get it permitted. We filled that up and completed it about 2 or 3 years ago, and there was no question we would never be able in the national park to get a number 5 settlement tailings dam permitted. It would have cost millions and taken years, and we had to. So we had to address the fact that we needed to go to process tailings, dry stack tailings, and I'm a great supporter in the northern hemisphere where it rains, where it snows in the winter, and the snow melts. That I believe now strongly that we should be, as a norm, processing tailings and not relying on settlement lagoons. And so what we embarked upon was we bit the bullet and said, let's install process tailings where we could operate that as an extension of our processing plant, not sensitive for permitting or regulation. And we came up with a design where we effectively looked at it, and in our tailings, we looked at splitting the size fraction, the plus 45 micron component of tailings and the minus 45. Now, the plus 45, the granular tailings presented less of a challenge. And we went to Ireland for quarrying equipment and technology, and we purchased there a basically screen and cyclone, which removed the coarse fraction very, very efficiently. Let me see if I can. So we effectively recovered the coarse fraction. These are some numbers we're using. The Irish basically hydroclones to set and achieve a coarse underflow of plus 45 micron and approximately 60% solids. The big problem we had was the underflow, where we, in effect, the minus 45 micron material. And this is the coarse fraction, where we're using cyclones and rotating screens. And as you can see, we can convey that relatively and put it into a coarse stockpile. The challenge was the fine fraction and the minus 45 material. And what we effectively went with there is still using quarrying technology, but we basically we thickened it, and then we used a belt press. Now, there was a lot of debate as to whether we'd be able to make the belt press work, but thickening the fine tailings before is really the key. And then we now successfully dewater the fine tailings. You can see here, and then they will come up and we stockpile those. What we then do is take the coarse and the fine tailings and we mix them, and we're getting probably a moisture of somewhere between 15 and 20%, which is enough to put it in a dump truck. And that's really what we wanted. And then we effectively take that to use it as a restoration material in our redundant quarries. Now that's a win-win as far as the park is concerned, or the national park, because we are effectively restoring standard quarries where the aggregate industry can't, because they take it all away and have nothing to put back. This is our main Longston Edge quarry, which is worked out, but as you can see, it's deep, narrow quarry, and it would be a challenge for long-term management in the landscape. And the object we tried to achieve was being able to restore it. Coming back, this is a description, a brief flowchart of our tailings processing sheet, which effectively splits it at 45 microns, where we then go through cyclones, dewatering screen, and the finer stuff is thickened and goes through a belt press, and then it's combined. This is what we're replacing in number 4, which is the traditional tailings lagoons, which we now is history for us. That is our redundant number 4 dam in the national park, where we're using it for water storage, so that we can recycle water from our tailings, from our processing plant, and we are self-contained. We have no discharge off-site. We reuse all the water. Here's just a few notes on the management and closure of our number 4 dam, which we're doing to a sustainable standard, and that's now in closure management. But coming back to the process tailings, we're now taking our dewatered dry stack tailings, which we campaign twice a year, and we then take it up, and we are backfilling and restoring our narrow vein quarry. And that is a very, very important point, because unlike the aggregate industry, we restore our open pit quarries, and therefore we can genuinely promote that what we are undertaking, mineral extraction, as a temporary land use, and we're putting it back, and we're only borrowing the land in the national park, and we are putting it back for future generations as a sustainable landform. This is again just some final pictures of our quarry workings and how we've put it back. A few notes on the restoration of our Longston Edge. We have a 20-year planning permit to restore Longston Edge with tailings, redundant quarry, and that is very important, because what it effectively does is that a lot of the mining industry will concentrate on the resource we're going to mine and explore and exploit. It then uses some clever things to work out how we extract the ore to a saleable product. But unless we can dispose of the tailings, particularly in Europe, particularly in a national park, forget it. We don't have a mining operation. And I would argue that management of the waste disposal is probably the most important part of a modern mining operation, and certainly is essential. You can't just throw it away and forget about it. You have to manage tailings disposal, and I think in the last few years, with some of the big issues of tailings dams around the world, I think the future of mining, particularly in Europe, particularly in environmental sensitive locations like a national park, the key factor is the closure, the restoration, the borrowing the land, leaving it in a sustainable manner for the future. And that means we have to improve our tailings disposal. And I'm firmly of the view, in the northern hemisphere, not in the desert, settling lagoons are great, but in the northern hemisphere, where we have a lot more rainfall and colder climates, processing tailings is now the future for northern hemisphere cold climate mining. Take it away. And that's pretty much a run through how we continue hard rock mining in the Peak District. We're one of the few mines still operating in the UK. I think we've got, we're small, but we've got a good term future. We understand the whole process. We cohabit in the national park well, and there is a strong demand for European sources of strategic raw materials because the fluorochemical industry and the chemical plants in Europe, we supply chemical plants in Norway, Germany, Italy, and throughout Europe in a smaller scale package. And I think there is a need for this strategic mineral to be mined in Europe, but we have to do it in a sustainable manner.